the whole purpose of this class is the interwoven nature of art and science, that are direct overlaps between calculus, linear perspective, and the concept of infinity. So I'm going to run through this somewhat chronologically, historically speaking. We're going to start with ancient Egypt, and what is important about ancient Egypt was just how numbers were used. So we are familiar with hieroglyphics, but the fact is that even though it seems like there's lots of things about people being mummified and things like that, it's all documentation of where someone was buried, how they were buried, what stuff they had with them when they were buried. It's all factual stuff. It's about land, where land is, how you measure land, who owns what land. It's facts. It's not a novel. It's not a fantasy. It's basically just that. And that's really significant and important. The other thing that's really important in terms of hieroglyphics is how it's set up. It's set up like a book that you read from left to right or up or down, right? It's literally from side to side is how you're going to read it. If there are pictures of people or if there are symbols, it's read, right? So that's something that is important as we move forward. So then we're going to jump from ancient Egypt to ancient Greece. I want to start with this guy. There's a lot of different Greek philosophers and mathematicians, but I want to deal with the fun stories first. So Archimedes. So the fun story about Archimedes, some of you probably know, is that there was a challenge where they were making this golden crown or a golden wreath, and it was questionable if it was really gold, if it might have just been silver that was gold plated, right? So this is a challenge that he was set with to say, can you figure out if the people that made this stole the money for the gold and actually made it only half with gold or not? So question, how do you figure out if it's really gold or not? Hard day of work, jumps in the bathtub, lays back, water goes up. And then he got super excited, jumped out of the bathtub and said, "Eureka!" Runs down the street without any clothes on, screaming, "Eureka, Eureka! I've found it, I've figured it out." Figured out how to gold in the crown or not, right? The way that he did that was buoyance, this basic principle of buoyancy. So if you have an object that sinks, it is heavier by comparison to the water. If it rises, if it's lighter, it's going to float. And if it's the same, it'll stay in the middle. So when he took the crown and put it in, basically it's the same shape, form as a piece of gold, a piece of silver, and then the crown itself. Displacement of water, what basically meant what it floated, was different, determining that the crown itself was made not 100% of gold. But this is one of the early first steps in understanding and talking about calculus. But more specifically, he wasn't thinking about calculus back then. What was key then was this idea of displacement. What's not in the tub, and then all of a sudden you put something in the tub, the water goes up, right? That space that was filled, that is going to be significant for us as we move forward. Ultimately, if one measures that space of the water in the tub that filled up, you're able to basically cut that piece out, sew it back together, piece it back together to get something that's easier to calculate, like length and width, to get an area. That's an easier one. But if it's an awkward shape, you might cut it apart and then place it back together to get a more manageable. In that time period of ancient Greece, they had a limited number of shapes, and they loved shapes and forms, right? This simple Euclidean geometries, they dealt with circles and ellipses and spirals and so on and so forth. There are different groupings of them, and some had different hierarchies. Circle is the highest in terms of forms that they were interested in working with or investigated. All of these forms will come up again. specifically in this area with the ones that seem to be the most relevant, what fits into a cone, right? So this idea of the circle or the ellipse. This is a little bit of the cutting and splitting that I was saying. So you take a simple circle and then you put something in the circle, you want to be able to measure it. For this shape, how are you going to figure out the surface area? What you can do is you can divide that up into triangles. And then easily those individual triangles, you can cut them apart and reform them into rectangles. And to try to get closer to the surface area of that circle, right? This is the problem with pi r squared, is that you can divide that more than just 5 sides, then you go to 12 sides, and then you go to many, many sides. And then you're getting to this point where you're coming really, 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 really close to becoming a circle. But it's not quite a circle. It's still a little bit off. And that's where this comes into play. The challenge of infinity. Early on, way back in ancient Greece, up until, well, calculus, infinity was taboo, forbidden. It was something that you did not do because you cannot prove it. There's no limit. It's infinite, to be redundant. An example is this guy Zeno. Zeno's paradox. The point of Zeno's paradox is it's infinite. Anytime you have a length, you can infinitely cut it in half again. So this is one of the reasons why in math they said infinity are taboo, because it's not provable, it's not concrete, it doesn't have an end, there's no limit. This infinitesimal method discovery towards this idea of exhaustion, which is what we just did when we took that pentagon form and then divided it until you get the really, 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 really close to the point of exhaustion that you're coming darn close to that surface area, right? That's basically what this relationship is of discovery to proof. And that's what we were just talking about in terms of limits. There is a limit because you're able to stop at some point. So from this basic time period, from when dissections breaking things down, actually there's examples of where land masses property in ancient Egypt also were using these idea of dissections and then pasting them back together to figure out land masses or properties to the point of exhaustion of what we just said, divide, 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 divide. There is about 2,000 years between these developments that they did in ancient Greece to the point of what we're going to start talking about today, leading to calculus. 2,000 years. Huge gap. The irony is that from 1600 to 1665, 65 years, this huge jump happened like that. Now, in terms of linear perspective, how this is interwoven, I'm going to put my finger right here. What I'm proposing contributed to this. Now we're going to jump to the art part. Remember I said it's interwoven. So that was a little bit of math, a little old math. Now we're going to talk about the medieval Gothic time period. And that started off with the Gothic proto-Renaissance had artwork that looked nothing like hieroglyphics, right? But it functioned the same way because all of the figures are stacked side by side, one on top of another. It's a story that you can read from left to right. Who's the saint? Who's the donor? There's a story to be told, but it's a story that you can read. Right? This is also at a time period where a lot of people were illiterate, and it was the best way that people could understand stories, by seeing them, because they weren't able to read them. This is how they read them. And this is the way a lot of this proto-Renaissance art functioned. Now, moving that forward, you have people like Giotto, who was also of this Gothic proto-Renaissance time period. And you can see there's a story here that you can read left to right, and you see the figures are stacked. But this guy started doing something a little bit different. If you look at what's in the background, he has these little houses, and he starts to put all these little twists and turns and corners, almost alluding to that there's a sense of length, width, height, dimension, which pretty much didn't exist beforehand. I don't want to completely eliminate when I say beforehand. So I mentioned before, the ancient Greek time they did that. Also in other places in the world, they would use things that were using parallel lines that gave a sense of space and dimension, but not in a systematic way. Even if you start to look at those stairs, I don't want to walk up those stairs. It looks like I'm going to slide right back down, right? So there's nothing really very systematic or organized yet. So then we move forward to the Renaissance, and we have this fantastic story about these doors, the gates of paradise. So there was a small baptistry in front of a church, a cathedral that was not yet finished. They couldn't figure out how to make the dome. And they had this little baptistry, and they had this giant competition. The giant competition was to say who is the best artist in Florence that's going to make the sculptures, these relief sculptures for these doors. Well, it got boiled down to two artists. One of them was this guy, Lorenzo Ghiberti. He won, and the guy who lost his name was Brunelleschi. He was devastated because there was so much hype that he had to leave Florence. He left because it was too much to bear that he lost. So he left and went roaming through all of the ruins of ancient Rome that were in Italy, and he started doing some drawings of them. Now, observationally, right, this is one of those things that's really important, is what you see. He realized that when there's a column, what do we know about parallel lines from Euclidean geometry? Parallel lines never touch, right? These columns are parallel, the lines should never touch. Why is it then, when I'm looking at a column that has fallen, what's closer to me is bigger, and what's further away is smaller, and when I extend the lines of this column, those parallel lines that are never supposed to touch, they touch, they converge. There is a point of convergence at the horizon. The horizon is set at the eye level, and that was the foundation for building what is known as linear perspective, where parallel lines recede to what we call a vanishing point. There was lots of experiments with this, how he was developing it. He would do this thing where he would look through a mirror, see a reflection of his drawing, and he would see the actual object through the line of sight. That line of sight then ultimately translates to the eye level later. And that's how he was developing it early on. But then it became more systematic. The main and most important thing is that you have one point that's vanishing, one point that they all come to, one infinite point where these lines, for all intents and purposes, continue on forever and ever and ever and ever, right? You stop them, you create a limit at one point. Now, what is closer is bigger, and what is moving away is systematically getting smaller in a measurable way. One of the things that was quite interesting and unique about Brunelleschi is that after developing that linear perspective and bringing it back, and all of the artists were thrilled and using this technique, and it was really, really, they were still faced with this huge problem that this cathedral, so this is the baptistry is over here, this little tiny thing back here is the baptistry, and this giant cathedral was not finished yet. And then Brunelleschi said, I can do it. So there was another competition. He said, I can make the dome. What they were doing before was they were building up like piles of dirt and then putting bricks, and then they would take the dirt away and they would all fall in, right? And they were trying to mix the cement that they were using in ancient Rome. They weren't getting the mixtures right to hold the weight. It wasn't doing it. So they were not able to figure out how to make that dome. So what Brunelleschi figured out by all of his research, similar to what a barrel does, when you have a barrel, you have individual slats of wood, and then you're putting a metal band around the top and a metal band around the bottom, and it's holding it all into one place. With all the pressure from the wine that's in there, it's not going to explode, it's going to be held in by those rings. So what he did was he created chain circles that all of the bricks were built on. So there would be a row of chains that were linked as a circle, and then they gradually would get smaller as the dome rounded to the top, holding all of the bricks in place. Moving back to perspective, other people were still using perspective in different ways, and you had these, this is like 50 years later. People are still, wow, this is a fantastic tool. I can make it look like they're in a real courtyard plaza, and people are, but the thing that's interesting, ironic, is that things don't move so quickly, still was stacking people in a row, right? Even though they're in this great space. And oh, look, he's going to put people back there. They're further away, so they're smaller, but they're still stacked in a row, right? So this is just an interesting relationship of moving things forward. So as we're trying to move things forward, so we have Jan van Eyck. There's another artist with the Arnolfini wedding, because one of the things that's interesting, this is just a few years after Brunelleschi developed linear perspective. If you look at this really closely, in the background there's a mirror, and in perfect linear perspective, you have a reverse of everything you see in that room put off into the distance in a very measurable way. Here's another example of linear perspective. Also, this is Da Vinci as well, the Last Supper, plus the atmospheric perspective. You can see what's in the background is actually a grayer, cooler background. Those windows are framed out and fall into the background, as opposed to the figures in the foreground are much more, showing much more contrast. And there's this example of linear perspective where you have these lines that are receding and converging at one central point. The interesting thing that's about this one, which Raphael painted, was not just the composition and the linear perspective, but the subject matter. The subject matter is the School of Athens. This is at the height of the Renaissance, 1500, where you have the church was big and strong. You had a few years prior to this, right? This was about 1500, 1492. That was the Age of Discovery. This is also the beginnings of the Age of Inquiry, or otherwise known as the Enlightenment. So these are a couple of things that are important. What's interesting and significant, this painting was done in the Pope's personal apartment, right? A painting of a bunch of ancient Greek philosophers, where by chance, the book that Plato is holding is Timaeus. Timaeus was a book basically of numbers, of math, that broke down how the world is built, how the universe functions based on numbers, how it can be broken down into simple forms, and that is the building blocks for the world we live in. Very, very, very different than, Adam and Eve and Genesis and all that stuff, right? Very, very different. But this was, interestingly, at that time where there was a shift and definitely a contrast. So in case you're not familiar with Plato's Timaeus, one of the things that Plato writes about are these Platonic solids, these 5 solids, that any one of these individual forms can fit evenly into a sphere where every individual point will touch one aspect of that sphere. And those are 5 forms that potentially can do that. Discovery, what happened? You get a lot of people going out in boats. They need to navigate. They get lost at sea. They aim for India. They end up in the Caribbean. And that is done by measuring things, measuring the stars, measuring your location, planning for those kinds of things. That is not only in measuring us on Earth, but it's also heavenly bodies, meaning stars, planets. So Kepler. So one of the key things that Kepler contributed was ellipses, right? So this is an interesting thing going back to the ancient Greece, was circles, and the ellipse, really, really simple form. One of the things that was really, really key was that the orbit of planets didn't just go in a circle. They went in an ellipse. That was one of the key things. Second key things, we're going to give Copernicus a little bit of credit for putting the sun in the middle of our planetary system, right? Because beforehand, right, Earth was the center. That's what the church said, right? We're the center of the world. This is where it all starts. So that was a huge shift, and using that shift, placing the sun in the middle, was something that Kepler started playing with. And then he was getting fascinated with your friends, the Platonic solids, and realizing that there's a certain spacing and there's a certain, just like, remember our old friend Pythagoras and harmonies and ratios, right? Playing with these different things. There's a certain harmony that is intrinsic to the universe. That's something that Kepler really liked, this idea that you can get to the sense of the source of, well, God, like how things are built. Through numbers, we can discover how things are built. That's kind of what Plato was saying, too. He developed this system using the Platonic solids that there was a certain spacing between these orbits that were specifically tied to harmonies, right? Proportions. This is not accurate. So this was his idea, and it was ultimately wrong. This is one of my favorites that he got right. He liked to drink wine. He did a whole thesis on the geometry of wine barrels. 1615. Now remember, this is 150 years after Brunelleschi. He takes this wine barrel and he realizes, so just like Archimedes was able to measure the amount of displacement, you're able to measure within a barrel, let's say one sheet of paper, right? One plane. And then you can measure all of them, and if you're able to figure out the surface area of all of them, add them all together, then you can get the full volume of what's in the barrel. Right? That's a simple version of it. This was basically taking this idea of exhaustion and pushing it a little bit further. This is what's leading towards calculus. So then you have Galileo. So one of the things that was significant for us, for this group of talking about, remember how one of the things that perspective does, linear perspective, is that you can anticipate how far something is in the distance, exact placement. This is a cannon, by the way. They were only really able to figure out that it goes up and then it comes down, right? So you got this little, there's never really this sense of anticipating that there's an arc and where that cannonball will land. But this had everything to do with measuring the planets. It has a lot to do with relating these very, very simple geometric forms. So that pretty much was my big overlap in those areas with linear perspective. One of the things that perspective does not deal with so much in those sense of is time, but I'll explain that at the very end when it does. But one of the things that's key for calculus is this relationship of change, of how geometries can be used to measure changes, change in something. So change distance and time. So this is one really, really simple, I think, good example. So you have a cart that's going, you don't know, you could easily measure, okay, if the cart goes from here to there in a certain amount of time, you take the distance and you take the speed, you can get the overall, the speed versus times the time, you can get the distance, right, by putting these things together. But then what happens if the cart goes slow and then it starts going faster, right? Then you can divide that and say, well, you're going to take this one distance and then plus this distance, and you can get the total distance by adding them together. Quite simple in terms of, well, simple math. But then what happens if there's a certain level of acceleration? Then you can continue to subdivide, 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 add them together, add them. This is this idea of cutting, and I'm calling it pasting. Basically, cutting and stitching things together. You're going to cut each individual segment, add it together, add it together, add it together. This is one more step getting closer to calculus. So the fun part is what happens then when this cart is not going in a straight line. If the cart goes up, accelerates, comes down, and then loses its speed, and then has to accelerate again and comes down, right? That's another thing that you can just, if you can see these slides, subdivide, 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 and that's this idea of exhaustion that's happening. So this is basically measurable in all different forms, not just speed, but speed and distance. You can do it in flow, something coming out of like a faucet, and volumes. You can do it with power and energy, density and weight. There are lots of different things that can be measured with these really, really simple aspects. But we still didn't quite get to calculus yet. It's basically the tangent is marking the extreme, right? The high point, the low point. So marking that point by knowing where the specific tangent touches the arc, the curve. And that's where there's more things that are getting us closer and closer and closer. Basically being able to map those out in forms. The next step a little bit closer in this relationship, combining the geometries, basically all we've been dealing with so far is geometry and stitching things together with algebra. And that's where you have this guy, René Descartes and Fermat. They together started pushing this a little bit forward. And this is another little fun story for me. So all of you have dealt with, at some point, this Cartesian coordinates, right? So the Cartesian coordinates, x, y, the fun part of this story is how it was discovered. René Descartes, he's sick, he's in bed for an extended amount of time, and he's looking up at the ceiling, sick in bed, and then there's a fly in his room. So he's watching this fly fly around the room, and he realized, as he's watching this fly, I can always measure where that fly is in relationship to how close it is to the ceiling, how close it is to this wall, and how close it is to that wall. When the fly is over here, it just shortened that distance and lengthened this distance. That's the Cartesian coordinate system. That's how that was developed, by him tracking a fly in his sickbed. All right, so this we're talking about 1637. Again, 137 years after the High Renaissance. You're not seeing this slide very well. Doesn't matter. There's a lot of really famous mathematicians. Underneath it says specifically things that they did. I'm going to take a big, broad, quick step over that. Like I said, if you're interested in the history of calculus, there's a link. You can take a look at the video. I just want to talk about a couple of people that I think are significant. Napier is from Edinburgh. This is where logarithms start. Now, early on, when he first discovered these comparatives, logarithms is this Greek word logos, an arithmos, which is basically logos. Here it's calling it proportion, but it's basically, so let's just say proportionate numbers. That's ultimately what logarithms do. It's comparative relationships between those logarithms early on that Napier was initially doing were very, very practically used. It was basically a sense of using a calculator to do things more quickly, right? To add large numbers with simple comparative systems, basically, proportionate systems. But then it wasn't until 1685 who really discovered E, Euler's number, was not Euler or Napier. It was this guy, Jacob Bernoulli, but it was not actually made, it was not published until Euler published that in, 1736. That's really, really, really a long time later. So that use of between key points from Archimedes through Descartes, plotting, right, the coordinates, to the use of logarithms, is ultimately what led to, finally, and first, Newton with these reflexions, which was not, he didn't call it calculus, but independent, completely separate, in a different country, in Germany, he was in England. Leibniz discovered the same thing, and the number system, or the notations that we use, are still the same ones that Leibniz developed just a few years later. That's basically how you map out curves and what you use them for. Now, one of the things that I'm going to just end with is one of the practical uses, and this is one of the early things that connected for me the relationship to linear perspective. Because linear perspective is always this idea of a system that's going to tell you how far something is, how small something is. Now, in economics, you have this use of diminishing returns. Now, one of this diminishing returns is a simple way of saying it in practical language. If you buy a car, you drive off of the parking lot with a brand new car, it immediately decreases in value. You hold that car for a year, it decreases in value. You hold that car for 5 years, it decreases in value. There are systems to project what the cost of that car is going to be in 10 years. We know this, right? That's why they have like blue books, anticipate what the cost of a car should be based on how old it is. Not just cars, in real estate, in the stock market, in everything. This exists. This basic system is the same system that we use, anticipating how much something smaller will be as it progresses in distance, I should say, not time, in linear perspective. So that's the connection that I make.